UBC, and UVic.
So our aim,
So our aim is to bring the top experts in different areas of quantum computing, including both the software side and hardware side, to share the research with the quantum community in British Columbia. So our target is not only for established researchers, but also for students, industrial and commercial partners, and even government officials. So please feel free to spread the words for the upcoming interesting seminars. And furthermore, we still have a couple of slots unfilled in this fall. So if you have a favorite speaker, please let us know, and we will try to invite them to give talk. So to kickstart our series, it's our great honor to have one of the best speakers in the field, Professor Skull Aaronson, as our first speaker today. So Skull is the David Bruton Sentinel Professor of Computer Science at the University of Texas at Austin. He received his bachelor from Cornell and then his PhD from UC Berkeley. So Scully is a theoretical computer scientist, which mainly focuses on studying the capabilities and limits of quantum computers. So throughout his career, he has received many awards, including most recently the ACM Prize in Computing for his groundbreaking contributions to quantum computing. So I'm not a computer scientist, but his work is influencing even outside the field of computer science. So some of us may be familiar with the topic of boson sampling, and it is one of his very creative idea that is introduced in early years. So apart from an excellent researcher, so is also an excellent communicator. He has published an excellent book in quantum computing since Democritus, and he also maintains a very popular book that teaches us what a quantum computer can do and cannot do. I'm pretty sure some of us have already keep regularly updating his blog. So yeah, that's all for my introduction today, and I will reserve the time for Scott. Today he will tell us more about his most exciting recent research on shadow tomography. So let's join us to thank Scott again.
All right. Well, Caro, thank you so much for inviting me to this. You know, I have enormously enjoyed my visits to Vancouver. It's one of the most beautiful cities that I know anywhere, and I'm happy to even just be able to visit virtually. And hopefully, after COVID is over, I'll have an opportunity to visit in person again. So I you know, I've been giving like a ton of virtual talks during this pandemic about quantum supremacy, and it's, you know, apparent achievement a couple of years ago by a group at Google, and then a second claim by a group in China. I kind of got tired of that, so I'm going to give you a different talk about something that's also really close to my heart, and this is this proposal I came up with 5 years ago called shadow tomography of quantum states, and I'm pleased to see that this, you know, proposal, you know, actually kind of like boson sampling, which I proposed 10 years ago. My student Alex Arkhipov and I proposed it, and then, you know, we proposed it as computer scientists, and then the physicists got a hold of it and they made it into something of their own. You know, they made it into something actually, you know, quite different from what it had been. And I see exactly the same thing happening now with shadow tomography. But, you know, I will tell you my point of view on it, and then I'll say a little bit about some of the recent things that have happened. All right, so, you know, the starting point is something that you know, everyone who works with quantum mechanics knows very well. You know, one of its most fundamental properties, right? That measurements in quantum mechanics are inherently destructive. Okay, if we think about a qubit, you know, you know, people love to have this argument about how many classical bits, you know, does one qubit correspond to, right? And you could, you know, defend an answer of 1 because of Halevo's theorem. You know, you could defend an answer of 2 because, you know, you've got the, you know, the X errors and the Z errors, and you know, because of teleportation and dense coding and so on. You could, but then you could also defend an answer of infinity. Okay, a single qubit, involves, a pair of complex numbers, pair of amplitudes, alpha and beta, right? And to specify them, to arbitrary precision would actually be an infinite number of bits. But of course, we never see that infinity, right? An amplitude might encode the complete works of Shakespeare, in its binary expansion. But you would never see that when you look at the qubit, because you just get to make one measurement, and then you see this single probabilistic result. And then famously, the qubit collapses to whichever outcome you observed, according to the Born rule, like that. Okay. Now, this destructiveness is, a major limitation of quantum information, but it's also an opportunity, right? And, extremely early in the history of our field, even in the 60s, Stephen Wiesner noted that the destructiveness of measurement opens up cryptographic possibilities, like, what we now call quantum key distribution. Okay, quantum cryptography is entirely based on the idea that if that an eavesdropper cannot measure the qubits that are passing through a channel without disturbing those qubits in a way that the legitimate parties could then hopefully detect. Okay, likewise with quantum money, where we could make measurements to verify it, but if a counterfeiter is trying to make copies of money, then not only will they fail to make copies, but their measurements will even destroy the legitimate money that they had. Okay, so this is a really fundamental property of quantum information. But now just from a philosophical standpoint, it is really striking, and it becomes more so when we think, not just about one qubit, but about thousands or millions of qubits. Because in that case, even just to, if I have a state of, let's say, 1,000 qubits, then even just to specify that state approximately, forget about specifying the amplitudes to infinite precision. We're going to give up on that, right? But even just to specify kind of roughly where an n qubit state is in Hilbert space, that already requires a number of classical bits that grows exponentially with n. Okay, like 2 to the n. Okay, and the reason for that, of course, is that we could have arbitrarily complicated entangled states. Okay, states that look like this. The sum over all possible n-bit strings x of alpha x times ket x. Okay, so even to specify a state of 1,000 qubits, in principle, we need 2 to the 1,000 independent complex numbers. Okay, which, if we had to write them all down explicitly, that is far more than could be written down in the entire observable universe, which only has about 10 to the 80th atoms in it. Okay, so so nature somehow has this, absolutely enormous scratch paper, that we never get to see, right? That is maintaining all of these amplitudes, and then we look and we just see a single probabilistic sample, right? And of course, this was the observation that in the 1980s led Richard Feynman and David Deutsch and others to originally propose the idea of quantum computation. Right? That if nature is doing all of this work behind the scenes, maintaining this exponential list of amplitudes, then why not try to take advantage of that, right? Or, as I say, why not take that computational lemon, that nature is so hard to simulate, apparently, and make lemonade out of it. Okay, but, we know from the famous Halevos theorem that if I measure a state of n qubits, there's a sense in which I can at most learn n classical bits of information. Okay, so if Alice sends n qubits to Bob across a channel, then Bob, by measuring those qubits, can at most learn n classical bits that Alice wanted to send. or 2n bits if Alice and Bob were lucky enough to pre-share entanglement. Okay, so but there is no protocol for sort of packing an exponential number of classical bits into a small quantum state and then unpacking it, and then reading them all out again. Right? That is something that's not possible. Okay, so to me, this state of affairs, raises philosophical questions even. Should we say that these amplitudes, these 2 to the n complex numbers, are really out there, in a single copy of our n qubit quantum state? Or should we think of them as just being in our heads, as just, a bookkeeping device that we use to calculate the probabilities of the different measurement outcomes? So now, an extremely instructive comparison is to think about just a classical probability distribution over n-bit strings. Okay, now that also requires 2 to the n parameters to specify, right? Just to specify a distribution over n-bit strings. Classically, already I need 2 to the n or 2 to the n minus 1, let's say, real parameters. But in that case, none of us really think of all those parameters as really out there in the world, right? We say, well, you can look at your string and then each bit will either be 0 or it will be 1, right? Really, there is some definite state of the bits, just that if you haven't looked at the bits, then you don't know. And so you describe your own ignorance using this gigantic object called a probability distribution. But then, as soon as you look, then you see the actual state, and you see that the probabilities in some sense were never there. Okay, now of course amplitudes can interfere with each other, right? And amplitudes can give rise to different probability distributions depending on in which basis we choose to measure the state. And so it seems like with amplitudes, we have to think of this exponentially large object as at least a little bit more out there in the world and a little bit less just inside of our heads. Okay, but to me, the best thing to do with a philosophical question is to try to use it as inspiration for technical questions, right? That ones that you could hopefully answer. Okay, and so this I've just come back again and again to this question of sort of how much information is really there in a quantum state for the last 20 years almost, and have tried to come up with sort of technical versions of that question that one could make some more progress on. So one very useful way to think about what we're trying to do here is quantum state tomography. Okay, now this is the task where we have a machine that can generate a quantum system in some quantum state. Okay, and we'll imagine, because we're going to need it, that the system can generate many identical copies of the system in the same quantum state. Okay, and let's now be more general and let's think about our state as a mixed state, rather than just a pure state. Okay, so we'll think about our system as being specified by a density matrix, rho. So D by D, trace 1, positive semi-definite Hermitian matrix. And now let's say that our goal is to learn the density matrix. So we want to learn what is the quantum state of our object. Okay, we can now ask the question, well, how many copies of the state do we need in order to solve that problem, right? And that's such a basic question that it's astounding in a way that this question was only really solved like 5 years ago. Okay, and the result was that the answer turns out to be that about d squared copies of the state are both necessary and sufficient for approximately reconstructing the density matrix under basically any reasonable notion of approximation that you could come up with. Now this is intuitively kind of what you might have expected, right? Because after all, a density, a D by D density matrix has order D squared independent parameters in it, right? And each copy you might think of, will give you only a very small number of parameters when you measure. And so, intuitively, it seems like maybe you should need D squared because you're trying to learn D squared matrix entries. Okay, but neither the upper bound nor the lower bound is entirely obvious here. Okay, the obvious upper bounds would give you something like D to the fourth or D cubed. And to actually get a protocol that reconstructs an unknown state using only D squared copies of it, it actually required very sophisticated representation theory. And actually the algorithm is, we still don't know how to do it via an algorithm that is computationally efficient, right? So this result is only information theoretic. It says that there is some measurement you can make on D squared copies of the state that will recover the density matrix, but we don't know how to implement that measurement in a reasonable amount of time. And then, the lower bound is a little easier to prove, but, one can use information theoretic arguments there. But, now, you might say, the really important point here is not whether it's D squared or D cubed, right? It's just that it is some polynomial in D, D being the Hilbert space dimension, okay? And, as I said, the Hilbert space dimension, we think of as an exponentially large quantity, right? It is exponential in the number of qubits n, right? And so basically we're saying if I want to learn an unknown state with, 100 qubits, I need something like 2 to the 200 power copies of that state in general, right? So an utterly ridiculous number, okay? And, this helps to explain why, the world record, I believe, for doing full quantum state tomography, with a state that you knew nothing about a priori, was to do it for a 10 qubit state. Okay, this was done just 4 years ago. It required, you looking at millions of different measurement settings. I don't know how many grad students were involved in, in doing this, but this is something you definitely don't want to scale this to 20 qubits, right, or even to 15, right? This is just clearly becoming infeasible. Okay, so that's part of what motivated me 5 years ago to introduce this notion that I called shadow tomography. Actually, I had a much worse name for it, but then it was Steve Flamia, a physicist, who suggested the name shadow tomography to me. I think, physicists are just much, much better than computer scientists at naming things. You've got, black holes, quarks, the Big Bang, right? We're stuck with non-deterministic polynomial time. Okay, so all right. So what is shadow tomography? So what I said around 2016 was, well, suppose that we've got a bunch of copies of some unknown quantum state, but now we also have a list of measurements. Okay, so a priori we know a list of measurements, which I'll think of for simplicity as just 2 outcome measurements. Okay, so they either accept or reject. They're 2 outcome POVMs, if you like, and let's say these capture those aspects of my state that I care about. Okay, so what I want is not necessarily to learn the entire density matrix, because that might be hopeless. I want to learn the behavior of the density matrix with respect to these measurements. Okay, but there might be an enormous number of these measurements. Okay, and I want to know the behavior of my density matrix with respect to all of them. Okay, and I had a bunch of reasons for caring about this question. It came up in understanding schemes for quantum money, for quantum software copy protection, for a bunch of other things. But you could also imagine lots of situations in experimental physics where you have some list of observables that you care about for your state. Maybe they're the k-point correlation functions. maybe they also include some, something more interesting, some more non-local observables, right? But you have a list of observables that you care about, which is short of every possible observable. Okay, and now we could ask the general question, well, how many copies of rho would you need in order to estimate the expectation value of each and every one of these observables on your unknown state? Okay, so let's just make some immediate observations about this question. Okay, so clearly, it would be enough, if I have enough copies of rho to do full quantum state tomography of rho, well, then that obviously suffices, right? Then, once I've learned rho, then I know rho's expectation value on any operators that I want. So we could say clearly d squared copies would suffice. But now there's a completely different regime of parameters, that is also relevant here. We could say, if I only have a small number of measurements that I care about, let's say if m is small, I also know that only m copies of rho will suffice, because I could always just apply each of my measurements to separate copies of rho, right? And I'll destroy the copies as I go along, but I don't care about that because I've got more copies, right? So roughly m copies, where m is the number of observables, would also suffice. Now, the question that I ask is, well, what if d and m are both enormous? Like, in many of the cases I care about, they would both be exponentially large. It would both be exponential in the number of qubits. And so, d squared is too much, m is also too much. And so I asked the question, could there be a general procedure for doing this shadow tomography using a number of copies of rho, which would grow polynomially only with log d and log of m? Okay, so even if d and m were both exponential, could I do this with a number of copies of rho that was only polynomial? Okay, that's a way to think about this question. Now that seemed like too much to hope for, and so I spent a bit of time trying to prove a lower bound that would rule this out, show it impossible, show that it would conflict with Holevo's theorem or some other principle of quantum information, and I couldn't manage to do that. I could not rule it out. And so then in a paper in 2018, what I did is I finally explained why I had been unable to rule it out. Okay, and the reason why is that it is possible. Okay, there is a protocol that actually achieves this. So in the 2018 paper, I gave a protocol for shadow tomography that estimates, the acceptance probability of each measurement E sub I to within an additive error of plus or minus epsilon, using basically this number of copies of rho. Okay, so it's log of m to the 4th power times log of d divided by epsilon to the 4th power times some much lower order terms. Okay, so this is not in fact, we now know that it's not optimal. This can definitely be improved upon. But this showed for the first time that this sort of shadow tomography, at least information theoretically, is possible. Okay, so what are the implications of this? Well, one way that I like to state it is, if you're given an n qubit state psi, then for any fixed polynomial p, by measuring only a polynomial number of copies of psi, you can learn psi's behavior with respect to every possible quantum circuit with at most p of n gates. Okay, where behavior means like approximately what is the probability that that circuit accepts the state or rejects the state. Okay, so it says, maybe, you're not going to reconstruct your full quantum state psi, but if you just want to know, like, what does every circuit with at most n squared gates do with psi? Does it probably accept psi? Does it probably reject psi? You can figure that out by measuring only a polynomial number of copies of psi, even though there are exponentially many different circuits with n squared gates. Okay, another implication, if I give you a quantum program, say rho, so meaning, a quantum state with some polynomial in n number of qubits, which you can use, you can feed into a quantum computer as a piece of quantum software, right? So like a thing you could use to sort of, maybe you buy it from the quantum software store and you bring it home and you use it to enhance the power of your quantum computer, give it some capability that it didn't have before. Okay, so then what I claim is that if you bought just a polynomial number of copies of this software from the store, then information theoretically, you now have enough to determine what that software does. Like, does it accept, does it reject, on every possible n-bit input string X. Okay, and that's despite the fact that there could be inputs where it's just sort of on the knife edge between accepting and rejecting. It might accept with probability half or something like that. So a consequence of this is that if we wanted, I talked before about quantum software copy protection, which is the idea that you would give someone a quantum state that they could use to calculate some function, but they would not be able to make copies of the state to give to their friends that would let to let their friends also calculate the function, right? So this is an application of quantum computing that maybe Microsoft or would be enormously interested in, or any other software company. If you could get this to work, and I and others have done a bunch of work trying to come up with schemes for quantumly copy protecting various functions. But these schemes are basically all based on some sort of cryptographic assumption, right? So in addition to the no cloning theorem, in addition to the destructiveness of quantum measurement, they are also relying on cryptography to just make it intractable for a counterfeiter to make, for a software pirate to make copies of the state. And what shadow tomography is showing is that reliance on cryptography is really necessary here. Okay, because a software pirate who had unlimited computation time really could make copies, really could pirate any quantum program. Okay, now I hope that shadow tomography will also find applications to experiments, and that is just starting to happen now, partly because of this work by Huang, Kueng, and Preskill just a year or two ago, which recast shadow tomography in a more physics language, and people are now sort of just starting to do some actual experiments that involve sort of constructing what they call a classical shadow of a quantum state. I hope that will actually be useful for something. Okay, so in order to explain how shadow tomography works, a crucial concept is that of gentle measurement. And I think that this was originally introduced by Andreas Winter in 1999. I had a different variation of it in 2004. And then, Mark Wilde has I think maybe the tightest version of it. But basically, so you may have heard of the information disturbance trade-off, right? That says if you make a measurement of a quantum state and sort of nature has to generate a lot of new random information in order to, give you the outcome of your measurement. Like, for example, if you take a qubit that's in the plus state and you measure it in the 0 and 1 basis, then necessarily that measurement will also disturb the state by a lot. Okay, gentle measurement is the converse of that statement, which is also true and which is extremely important for many, many applications in quantum information. So gentle measurement says if you make a measurement of a quantum state, and if knowing the state and knowing the measurement, you could almost certainly predict the outcome of that measurement. Let's say, like your state was close to an eigenstate of, of whatever measurement you were applying, then that measurement can be implemented in a way where it only damages the state very little. Okay, where after the measurement, you have almost the same state that you began with. Okay, so formally, so we say, suppose that we apply a measurement to a mixed state rho, and suppose that a certain outcome is obtained with overwhelming probability, like at least 1 minus epsilon. Then after applying the measurement, we can recover a state, say rho prime, which is very close to rho in trace distance, the usual metric on quantum states. Let's say, its trace distance from rho is at most square root of epsilon. Okay, this is the gentle measurement principle, right? So basically, if your state is close to one of the basis vectors, then it probably just snaps to that one, and then it is only damaged very slightly. Okay, and something stronger is true, which is I could apply a whole sequence of measurements in succession, and let's say that each of them has the property that it yields an almost deterministic outcome when applied to my original state rho. Okay, then this thing that I've named the quantum union bound says that if I then apply that entire sequence of measurements to rho, one after the other, then the total damage to rho in trace distance grows at most like m times the square root of epsilon. Okay, so the error sort of only builds up linearly over time, right? I can apply a whole sequence of measurements, and as long as each one individually wouldn't have damaged rho by very much, then even the whole succession of them won't damage rho by very much, as long as there's not too many of them. Okay, now this trick of gentle measurement is very often combined with amplification. Okay, amplification means I can always if I have many identical copies of my state, and let's say that a measurement on any one copy would yield a certain outcome with a 90% probability, then with k copies of the state, I can apply what we would call an amplified measurement, which means I coherently measure all k of my copies, and I ask, well, what is the majority outcome, among all k of the measurements? And now I just appeal to the Chernoff bound, as a computer scientist would say, or concentration of measure, right? I say, look, the probability that I can now estimate the expectation value of my observable, given k copies, and the probability of a large deviation away from that expectation falls off exponentially with k, exponentially with the number of copies. Okay, so I can first use amplification, many copies of my state, to push the epsilon, push the probability of a bad measurement outcome down to being exponentially small. And then I can use this gentle measurement to say, and therefore the damage to my states each time I apply a measurement will only be by an exponentially small amount. So I must have 10 papers where I use this combination of tricks in order to get around the destructiveness of measurements in quantum mechanics, right? And apply many measurements to the same states, while only damaging those states by a little. Okay, so all of this raises an obvious question, which is, why can't we just use gentle measurement to immediately solve the problem of shadow tomography, right? I've just shown you these tricks. Why can't we just use them to, estimate, each expectation value that we care about, for each observable, for our state rho using several copies of rho, And each time we do it, our copies of rho will only be damaged by a tiny amount. And so, we'll be good. Why aren't we done? Well, here is the problem. So it turns out that the gentle measurement does immediately give you shadow tomography, but only in a special case where we have what is called a promise gap. Okay, so here is what you can get immediately. We can say, given a bunch of 2 outcome measurements, E1 up to EM, and given some real numbers, let's say C1 up to CM. Now, if we are promised that the expectation value of each measurement, EI, is either at least C sub I or else at most C sub I minus epsilon, so, and it's not in the intermediate zone between the two, then I can, for each EI, I can figure out which side we are on, right? And I can do that using a number of copies of rho that grows only logarithmically with the number of measurements M, right? And I do this, exactly using the trick that of amplifying, amplification of measurements, and then gentle measurement. Okay. The problem is, this requires what I call a promise, right? I have to be promised that each expectation value, is not in this intermediate zone, between CI and CI minus epsilon. Okay. The trouble is when we don't have a promise, then for all we know, when we try to estimate some observable, like we can try to sort into 2 different buckets, like a yes bucket, where the expectation value is large, and a no bucket where the expectation value is small. But there's always going to be some little window in between the yes bucket and the no bucket, where the expectation value has some intermediate value. And for all we know, we might be in that intermediate zone. And there, applying the measurement is actually dangerous. Okay, so, it's not just that it won't give us a good answer. It is that applying the measurement, if we're on the knife edge between the 2 regions, will actually just destroy the copies of rho that we already had. Okay, because if I'm not, amplification will then not get me close to a definite yes or a definite no, and so I'm just in the usual situation in quantum mechanics when I am making a measurement of a state in the wrong basis, and that measurement can then destroy my state. Okay, make the information inaccessible. And I can afford to destroy some copies of rho, but I can't afford to destroy that many. Okay, because after all, I only have a number of copies of rho that is like polynomial in log of m, and I'm trying to learn m different pieces of information about rho. Okay, that's the difficulty. So the whole contribution in my 2016 paper was to solve that. Okay, so the proof combined several different ingredients. The first of the ingredients was a much earlier theorem that I had from 2004, which I called the post-selected learning theorem. Okay, and there I was interested in the following scenario. So let's say Alice is trying to describe some quantum state rho to Bob, with respect to its, and she's trying to describe the state well enough that Bob could estimate its behavior on m different observables. Okay, so this sounds a lot like the shadow tomography problem, right? The difference is that now Alice actually, she doesn't just hold rho, she knows what rho is. So, she just knows a classical description of rho. Okay, but still the question is, she can only send a limited amount of information to Bob, like much fewer than m bits, right? So how can Alice actually describe to rho well enough to Bob that he can then figure out how rho behaves on each of these m different measurements? Okay, and I came up with a curious protocol for that. which, any of you who have studied machine learning might have heard of a technique called boosting, which is, hugely important in machine learning. And what I'm going to do is extremely related to that. It's also related to what's called the multiplicative weights update method in algorithms. Okay, but here's how it works. We start out with Bob making the most naive possible guess about what rho is. Namely, he guesses that it is the maximally mixed state. Okay, because why not? Right now he has got no information about rho. Okay, then what Alice is going to do is she's going to repeatedly help Bob improve his guess of what rho is by telling him kind of the most important information that she possibly could about how rho behaves on the measurements that Bob cares about. Okay, so what she's going to do is repeatedly, so now, if it happens that right now Bob has a guess that approximately behaves like rho with respect to all m of the measurements, E1 up to EM, well, then Alice can stop right now, right? Because, Bob doesn't have to learn rho as a state, right? He just has to learn the behavior of the state with respect to these m measurements. So if he's already got that, via some other state simulating rho, then he's fine. He's done, even if that state is very far from rho in trace distance, let's say. Okay, but what if we're not yet there? Okay, so what if Bob's current guess, and remember his initial guess is just the maximally mixed state. Okay, so what if his current guess leads to a behavior on one of these measurements which is very, very different from the behavior of rho, of the true state? Well, then Alice is going to help Bob improve. And the way she'll do that is by telling Bob, just one such measurement where he's currently getting a badly wrong answer. And on that measurement, she'll tell him what was the right answer. Okay, so, just, imagine a teacher helping a student improve, or imagine, Darwinian natural selection, helping a species improve, right? By just sort of repeatedly correcting it. Okay, so she gives him a measurement on which his current guess badly fails. And then Bob improves his guess by letting rho sub t be the state, obtained by starting with his previous guess, rho sub t minus 1, then performing the measurement that Alice told him about, and post-selecting on getting the outcome that Alice said he should get. Okay, so we just sort of assume, so post-selection just means you make this measurement and you just assume that you get the right outcome. Now, that would be a very hard thing to do if we were talking about measuring the actual quantum state. But Bob can just be maintaining a description of the state in his computer, right? And so then this post-selected measurement is just like a mental operation, right? It's just, a thing he can do to his description of the state, and that's easy for him to do. Okay, so he keeps improving his guess in this way with Alice's help. And now the key observation is that for sort of reasons that are understood in computational learning theory, this iterative process has to converge after a number of iterations that grows at most like the log of the dimension of the Hilbert space. Okay, so we only need a number of training examples that is linear in the number of qubits in rho. And then Bob must end up with some state that behaves on these measurements like rho. Okay, and you can there are several ways to prove this. I mean, but the way I proved it was just by taking the maximally mixed state, which is Bob's initial guess, and decomposing it as kind of a convex combination of d different states, d being the Hilbert space dimension, one of which is the true state, rho, right? And then you can say that the parts of the components that are not rho are sort of getting exponentially killed off with every wrong answer where Bob then post-selects on not getting that wrong answer. Okay, and until he has to stop either being left with Rho himself or being left with some other state that behaves just as well as Rho with respect to these measurements. Okay, so now I introduced this post-selected learning theorem just for reasons of quantum complexity theory. I was interested in this complexity class, which is called BQP/QPoly. BQP is bounded error quantum polynomial time, the class of all the problems efficiently solvable with a quantum computer. /QPoly means with a polynomial size quantum advice state, which only depends on the length of the input and not on the specific input beyond that. And so what I showed was that quantum advice can always be simulated by classical advice, which is only a little bit larger, provided that you're willing to use exponentially more computation time to decode what the classical advice is telling you. Okay, so this was kind of the first limitation on the power of quantum advice states. Okay, so can we use this post-selected learning procedure to solve shadow tomography? Well, unfortunately, it's still not enough by itself, because we relied on Alice knowing the state and just telling Bob, using her knowledge of the state to tell Bob which measurements would be informative ones to post-select on, to sort of improve his hypothesis of what is Rho. Okay, but in the shadow tomography situation, there is no Alice, right? There is no one who knows the state and who can tell you useful measurements to condition on, right? You just have these copies of Rho and you've got to figure it out for yourself. Okay, so then, my idea was to combine this post-selected learning with another result called the quantum OR bound. Okay, now the quantum OR bound is something that I had claimed to prove in a paper in 2006. And unfortunately, in 2017, Aram Harrow and Cedric Lin and Ashley Montanaro discovered that there was an error in my proof. My protocol might be fine. We don't. That's an open question. But the analysis of my protocol was wrong. But they gave a different protocol for which they were able to prove soundness. So they actually recovered this theorem, and I'm going to use that result as well. So here is the statement of the quantum OR bound. Okay, it says let Rho be some unknown mixed state, and then suppose that E1 up to EM are known two outcome measurements. Now suppose that we are promised that either there is some measurement in our list that accepts Rho with a very high probability, say, at least C, or else every measurement in the list accepts Rho with a small probability, at most C minus epsilon. Okay, the quantum OR bound says that it is possible to figure out which using a number of copies of Rho that is only logarithmic in M. Okay. Yes, that should not be obvious. And actually, the protocol that Harrow, Lin, and Montanaro give for this problem, it involves using a control qubit, where if the control qubit is 1, then you apply the measurements, and if it's 0, then you don't. You put the control qubit in the plus state, and then you kind of measure to see whether the control qubit has been decoherent or not. Okay, so it's a clever protocol. My protocol just involved applying the measurements E sub I in some random order. That's the one that we still don't know whether it works. Okay, so basically what I noticed in 2018 is just that you can put these ingredients together. So you can use this OR bound to repeatedly search for informative measurements. Okay, you can use it as a subroutine to repeatedly look for a, so your current hypothesis as to what is your quantum state. Let's say, rho sub t, where, initially your hypothesis was the maximally mixed state. And now you are searching for a measurement that you can use to improve your hypothesis, just like in that post-selected learning theorem. And so in order to search for that measurement that would, disagree with your current hypothesis by a lot, and which therefore will improve your hypothesis, you use this quantum Orr-bound procedure. You use this Harrow-Lin-Montanaro procedure. So it's like, the outer loop is the post-selected quantum learning, and the inner loop is the Harrow-Lin and Montanaro procedure. So putting all of that together, I got this protocol for shadow tomography that that had this sample complexity, like log of m to the 4th power times log of d. The to the 4th power really came from the need to do this Orr-bound procedure in the inner loop, and in particular to not just solve the decision problem of is there a measurement, but then to actually use binary search to identify that measurement. That's the next one that you should post-select on. That produced this blow up of this exponent of 4 here. And so it's interesting to ask, well, what is the right answer? How many samples are really necessary and sufficient for this shadow tomography problem? The best lower bound that I have been able to prove has been log of m divided by epsilon squared. Okay, and this is a lower bound that's got nothing to do with quantum mechanics. This holds even if I was just trying to learn a classical probability distribution, with respect to its behavior on various classical Boolean functions. Okay, even then I would need log m over epsilon squared independent samples for my distribution. Okay, and so you could wonder, well, in the shadow tomography procedure, does there even have to be any dependence on the Hilbert space dimension d? Right? Do I even need this log d factor at all? We still don't know the answer to that. Okay, well, but in a paper in 2019 with Guy Rothblum, we were able to improve the dependence on log m, and the way we did it was by making a brand new connection between the problem of gentle measurements of quantum states and what you might think is a completely unrelated topic in classical computer science, which is called differential privacy. And that's kind of a story in itself, right? Maybe since I'm running out of time, maybe I'll just say quickly, differential privacy is the a subfield of computer science that started around 2006, where you're interested in situations where like you have some database, some of like, let's say, very sensitive data, like people's medical records, and you want to allow researchers to query that database, but in a way that will not reveal too much about any one of the people, like whether they have prostate cancer or something like that. Okay, and so there's a set of techniques for dealing with this where you do things like deliberately add noise to the measurement outcomes before you return them. Okay, and so I gave a talk a couple years ago at the Weizmann Institute about gentle measurement of quantum states, which is a thing I've talked about in this talk. But how do you measure a quantum state? How do I measure a collection of copies of a quantum state in a way that doesn't damage them by very much? And I pointed out that one of the ways of doing that is to deliberately add some noise to the measurement outcome before you measure to get it. Okay, so for example, if I had an unentangled qubits, and let's say I just wanted to know the number of ones. So like I want to know, approximately what is, beta here, right? Or what is the amplitude on 1? Okay, well, if I just measure, all n of my qubits to ask how many 1s are there, that's going to be a very destructive measurement. Why? Because, you think of it as like the, this state here is some, if I look at the number of 1s, the total number of 1 bits, it's some Gaussian, right? It's some wave packet in physics terms, right? It has a mean, but it's also going to have a variance, of order square root of n, right? And if I measure to find out the exact number of 1s, then what I do is I localize that wave packet, right, to a specific number of 1s. Like I collapse it down to a specific Hamming weight. Hamming weight is just the computer science term for the number of 1 bits in a string. Okay, but there is a safer approach, which has actually been known for a while in experimental physics. And the safer approach is to deliberately add some noise to the number of 1s, before I measure, and then only learn that noisy number. Okay, so for example, I could add a Laplace noise, which is just noise that falls off exponentially, and and then I make a measurement where I only learn the Hamming weight plus the noise, and I uncompute everything else. Okay, and you can show that produces much less damage to the state. So I mentioned this in my talk, and Guy Rothblum, who's not a quantum person at all, but an expert in differential privacy, was in the audience, and he got all excited because he said, this sounds exactly like what we do in differential privacy. And I said, well, everyone listens to a talk and they think that it's, that it's connected to what they're working on, so it's probably nothing, but fine, let's meet for lunch and talk about it. And it turns out that he was exactly right. Okay, there is a direct mathematical connection between a differentially private query of a database and making a gentle measurement on an ensemble of quantum states. And we could prove that connection, and then we could even use it to do new things, and in particular to come up with a new procedure for shadow tomography that got some better parameters than what was previously known. Okay, so I'm going to skip this stuff because I'm running out of time, but this is just the formal definition of what we mean by differential privacy and the quantum context. And then the main result that we proved is well, it's this two-way connection between differential privacy and of a measurement and gentleness of that measurement. Okay, so it says that any measurement that is sort of alpha gentle on product states, meaning it damages more product state by at most alpha in trace distance, even after I condition on some outcome of the measurement, is also O of alpha differentially private on those states, meaning that like conditioning on the outcome of the measurement kind of reveals at most alpha information about, and conversely, any measurement that is epsilon differentially private on product states and that has a certain special form, we needed that, we don't know if this technical condition is actually needed, but we needed it to prove our theorem. Then it is also O of epsilon times square root of n gentle on product states. So there is some loss in connecting these two concepts captured by this factor of square root of n, but we can show that that factor is actually tight, so it is unavoidable. We have to restrict to product states, or else, we don't really get an interesting connection here. Okay, and so now I can tell you what is our new shadow tomography result, which is, we can do shadow tomography with this sample complexity. Okay, so you'll notice that the dependent, the number of copies is now not like log of m to the 4th power. It's only like log of m squared. So we improved on that aspect. We got worse in the dependence on log d, but there is some very recent work by John Wright and his student. I forgot to update the slide, But the recent work, and actually in the most recent stock conference, has improved this log of D squared to just log of D. Okay, so now the sample complexity of shadow tomography is really just like log squared of M times log of D. Okay, now our new shadow tomography procedure has some additional advantages. Okay, one of them is it is online. That means that you don't have to know all of the measurements, E1 up to EM, in advance. Okay, they can just be given to you one at a time, even by an adversary who sees everything that you're doing and is trying to trip you up, right? So someone gives you E1, you estimate, the expectation value of E1 on row, trace of E1 row. Okay, then the adversary gives you E2, you estimate trace of E2 row. The adversary gives you the third measurement, E3, you estimate trace of E3 row, and so forth. Okay, our new procedure can work like that. Okay, and our new procedure is itself gentle, meaning even after you finish the shadow tomography and you gather all this information about your state's row, your states are nearly undamaged. So you can now use them again for something else. Okay, our original shadow tomography procedure was not like that. All right. So, basically the way it works is that we took, some known work from classical differential privacy, actually work that Guy Rothblum himself was heavily involved with. And we came up with a quantum version of their algorithm, which we called QPMW, quantum private multiplicative weights. And then we used our connection between differential privacy and gentle measurement in order to prove that this QPMW procedure, was on each round was because it was private, because it satisfied differential privacy, it was also satisfying gentleness, and therefore it was not damaging the states by very much, and therefore we could really just apply all of these rounds one after the other, and get a shadow tomography procedure that was sound. There's like 30 pages of analysis to make what I just said precise, but that's the basic idea. So we studied also the computation cost of shadow tomography. All the procedures that we gave are, they're very efficient in terms of how many copies of row you need. They're not very efficient in terms of how much computation you have to do, right? Like if you want to know these M different observables, then the computation time grows, at least like M. And the computation time also grows like the dimension of the Hilbert space, right? And the trouble is, these could both be enormous, right? And so, I think it's a very interesting question. Can you get around that? Can you have a procedure for shadow tomography, which is also super efficient in terms of the computational cost? And I have some evidence that seems unlikely. It would lead to sort of breakthroughs in other problems if that existed. But we don't really know yet. Okay, and then the last thing I wanted to mention was this work by Huang, Kueng, and Preskill from just this past year. And they inspired by my shadow tomography work, they defined something called classical shadows, where basically they said, if you have a polynomial number of copies of some n-qubit state row, then you can measure something called a classical shadow. So there's just this one piece of classical summary information that you can get. And this is actually via a computationally efficient algorithm as well. So you just get this shadow, this little classical information, and then it is useful for answering further questions about row. For example, even if I have a list of exponentially many different pure states, I can use the classical shadow to estimate the fidelity between row and each and every one of those pure states. Okay, so I can't do everything that I could do with full shadow tomography, but on the other hand, their protocol is a lot more practical than mine was, or the measurements are easier to implement experimentally. So my student William Kretschmer this year came up with an application of classical shadows, which was simply to show that any pseudo-random family of pure quantum states can be distinguished from truly random quantum states given an exponential amount of computation time, which might sound natural, but we don't know how to prove it without using this classical shadows theorem. Okay. Now to make this stuff truly practical, we would like better sample complexity, better computational complexity, and easier to implement measurements. So, that was all I had. I apologize for going a few minutes over time. Thank you for listening, and I'm happy to take any questions.
Thanks, Scott, for the very inspiring talk. So is there any question? You can either type it in the chat, or you just raise your hands and or you just unmute and ask. So yeah, you can ask.
Yeah, thank you very much, Scott, for this very interesting presentation. I have one short question.
Sure.
Do gentle measurements have something to do with weak measurements?
Yeah, I get that question a lot. They do have something to do with it, right? Now it's very hard to articulate the exact connection because I have been unable to find a precise definition of weak measurements anywhere in the literature, right? But what we can say is that let me think about this again. So any weak measurement will also be a gentle measurement, right? But the issue is that there are measurements that are gentle on the set of states that we care about, like on many copies of the same state row, for example, or that are gentle on all product states, and yet that are very far from being weak. Okay, because like they actually do give you much more information about rho than any weak measurement could give you, right? So again, every weak measurement is gentle, but not every gentle measurement, or at least measurement that is gentle on product states, let's say, is weak. Okay, one can prove that every measurement that is gentle on all states is necessarily weak. Okay, but what we usually care about is we assume that we've got many copies of something. So like we know that we've got a product state, for example, right? And then you can have measurements that are going to be gentle on all states that are like that, and yet that are very far from being weak.
Okay. Do you have a concrete example of what's a gentle measurement, let's say on a specific hardware or quantum system?
Yeah. So precisely the example that I gave in this slide, right? Where you're, I mean, I talked about it as, measuring the Hamming weight of a string of n bits, right? Or, approximately by just, looking at the total number of ones and then adding some noise to it. If you wanted me to restate this in more physics language, you could say, I've got a collection of n spins, n spin 1/2 particles, and I'm trying to estimate, the average spin in the z direction or something like that, right? And I don't want to measure it exactly because that's going to, be very damaging to my state, right? But I can measure it approximately in a way that is not very damaging, right? I make sure to make a measurement of the total spin in the z direction with this noise deliberately added, in order to not be damaging to my superposition. Okay, this is a known thing in experimental physics, as I said, and this would be a perfect. This is sort of our canonical example of a measurement that is gentle on product states.
Okay, thanks. Thank you very much.
Sure.
Is there any other question? So I have a question. So to specify a shadow, so you need some classical description of the measurement PVM. So how does it sensitive to the classical description? Say, do you need an exponential more amount of bits to have to classify shadow or?
Okay. That's a good question. It depends on which of the results you're talking about. Like in in my original protocol for shadow tomography, I just kind of, because I only cared about the number of copies of rho, right? That was the only resource I was trying to minimize. And I said, just to solve that problem, let me assume unlimited everything else, right? So I said, just assume that you are given E1 up to EM, as D by D matrices, right? So you completely know them, right? And, you can take time that's polynomial in D, which is the Hilbert space dimension. You can do all of that stuff. Now, if you really care about computational efficiency, which I was, I just got out of the slide, but it's okay. If you really care about computational efficiency, then the question doesn't even really make sense unless you first say that the measurements have been described to you in some more succinct way, right? And so now there's several different options, right? Maybe my favorite option is to say you have a quantum circuit, right? And let's say I give you a small quantum circuit, and it takes two inputs. One input is rho, and the other one is I, right? And then this circuit will apply the measurement E sub I to rho, right? And so you could imagine that all of the measurements are described to you via that one small circuit that you are given, right? Mm-hmm. And you could then ask the question of, well, could I then, if I were given such a circuit, then could I solve the shadow tomography problem using computation time that was just polynomial in it, right? So that's in my paper, I called that possibility hyper efficient shadow tomography. Okay, right. That would be like really, like as long as the measurements were described to you efficiently, then you could solve the problem efficiently, right? That would be the goal. Okay. Unfortunately, I also pointed out that if hyper efficient shadow tomography is possible, then quantum advice can always be simulated by classical advice, right? BQP/Q poly would equal BQP/poly, right? And also copy protecting of quantum software would then never be possible, right? It would then always be easy to pirate a quantum state that you were given as a program, right? So it would have some fairly dramatic implications for some other questions, right? But maybe those dramatic implications are true, right? I can't really rule out hyper efficient shadow tomography, right? And I do still regard it as an extremely interesting question.
Thank you.
Yeah.
So is there any other question? Yep, please ask.
Yeah, I'd have a short one. It's at the very beginning of your presentation.
Yes.
When you say that a measure, I don't know if you could go back to that slide. It's
all right. Let me do that. Let me share my screen again, and
that's where you see you have a set of measurements where.
Where?
Yeah. Okay. Just let me see. Yeah. Whoops.
Here. Up here.
Before.
Here?
Two outcome measurements. Yeah, it's just to make sure that I understand them.
Yes.
So, so it's either each measurement is either accept or reject. I think it was before that, but
precisely. Precisely.
So,
yeah. That's right. And I mean the way to think about it is that just each EI is some operator. And the measurement accepts with probability equal to trace of EI times rho, and it rejects with probability 1 minus trace EI times rho.
Okay, but it accepts what precisely?
It by accept I just mean outputs yes. Output it just means returns the yes answer. That's all I mean by accept.
Yeah, but so you have a state and you do a measurement.
Right.
On that
and there
state.
are two possible outcomes of that measurement, and I call one of them accept, and I call the other one reject.
Okay. For instance, for a spin 1/2 particle, you say spin up is I accept. If it's not spin up, I reject.
Sure. For example,
As simple as that.
you get to define it to be anything you want. But yeah.
Okay, good. So
Yeah.
just you define. Yeah. Okay. I see.
Yeah.
Okay.
Yeah. Sorry. This is just computer science terminology.
Yeah, I know sometimes
When there's two outcomes to something, we call one
yeah.
of them accept and the other one reject.
Okay, good. Thank you.
Okay. Yeah.
Thanks.
Is there any other question? No, Eric?
Yeah.
Hello, Scott. Thanks for the
Hi.
nice presentation. I have a question about the slide where you show how to add Laplace noise to make the measurement.
Yeah, sure.
gentle.
Let's go down to that one. Here.
So it might be a naive question, but I was just
Right.
wondering, measuring the state, I think you call it with the number of ones.
Yes.
So sorry, are you measuring a specific state where all the outcomes are ones, or you're measuring of that state you have the amount of bits you measure with one as an outcome?
So I didn't understand the question, but maybe I can go through what you actually are measuring there. You are, look,
Yes, please.
you know, we have this superposition, right? Like sum over all x of alpha x x, where, you know, each x is a string of n zeros and ones, right? There's 2 to the n different x's. Okay. Now, the naive thing to do would just be to make a measurement that tells me the Hamming weight of x, you know, meaning the number of ones in x, right? That would be the naive measurement. Okay. We're not going to do that because that is destructive, right? That localizes the wave packet. It localizes the superposition over different Hamming weights to just one Hamming weight. Okay. The thing we are going to do instead is first prepare this superposition over possible values of eta, eta being our Laplace noise term, right? Then I am going to coherently, you know, so apply a quantum circuit that, you know, in some second register, in some ancillary register, writes Hamming weight of x plus eta. Okay. Then I am going to make a measurement that only tells me the Hamming weight of x plus eta. Okay. And all the other stuff, you know, any other work, you know, work that I did to get there, I will uncompute, right? I will run backwards to get rid of any qubits other than these qubits. Did that make sense?
Yes, that cleared it up. Thank you. I misunderstood something. Thank you.
Yeah.
Okay, is there any other question from students? So if not, I think it's a good time to end our seminar today.
Okay.
Thanks, Scott, again. So thank you. So hopefully we can get you.
For inviting me.
Yeah.
All right.
Hopefully we can get you physically in Vancouver sometime soon.
Yeah, absolutely. I would love that.
Okay.
All right. Okay.
See
Talk to you
guys.
later then. Okay. Bye.
Bye.